Okay, so what if I told you that our entire picture of the universe might be wrong? Not just a little bit wrong, but fundamentally wrong. We're going to talk about a radical new theory today, one that says the universe isn't just expanding into nothingness, but that it's actually alive, with a cosmic pulse, a giant, rhythmic heartbeat that could solve some of the biggest mysteries we've ever faced. So what's going on? Let's get into it.
For decades, we've had this thing called the standard model of cosmology. You can think of it as our rule book for the universe, and it's been incredibly successful. But, well, that foundation is starting to crack. Big time. You see headlines like this one from a French science journal, Le modèle standard s'effondre. It means the standard model is collapsing. And that's not just hyperbole. It's a huge sign that cosmology is facing its biggest crisis in 100 years.
So, why the crisis? Well, it's because our amazing new eyes on the sky, things like the James Webb Space Telescope and the DESI instrument, are sending back data that just doesn't fit. They've found that dark energy, that mysterious force we thought was just constantly pushing everything apart, well, it turns out it's not constant at all. It changes. It actually evolves over time. And that one little fact, it pretty much shatters the old model.
But what if we've been looking for the wrong thing? What if the problem isn't some missing phantom particle? What if the whole issue is how we're thinking about space itself? There's a bold new theory that says the universe isn't an empty void. It's more like a giant vibrating fabric, a four-dimensional membrane that has its own cosmic pulse.
Now, to get your head around a vibrating universe, you don't need a supercomputer or a PhD. You just need to look at this surprisingly simple and frankly beautiful old-school physics experiment. It's called a Chladni Plate, and it turns out it's the perfect metaphor for this wild new vision of the cosmos.
The idea is super simple. You take a metal plate, sprinkle some sand on it, and then you vibrate it with sound, like from a cello bow or a speaker. And this is where the magic happens. The sand doesn't just jiggle around randomly. It gets pushed away from the parts of the plate that are vibrating like crazy, and it all settles into these quiet spots that are perfectly still. It creates these incredible, intricate patterns, zones packed with sand and other zones that are totally empty, all created from nothing but vibration.
And here is the absolutely brilliant leap. In this new theory, our entire universe is the vibrating plate. And what we call dark matter, it's not a particle. It's not some mysterious stuff. It's just the effect of regular matter, stars and gas and dust, gathering in the quiet zones of the universe, the antinodes, just like the sand. But this raises a really cool question, right? If all the matter's in the quiet zones, what's happening in the nodes, the areas of super high vibration? And this is where it gets really, really exciting. Because this one single idea, a vibrating universe, starts to solve some of the most confusing and completely separate puzzles that have been stumping astronomers for years.
Okay, first up, the mystery of the impossible galaxies. Astronomers were just blown away when they found galaxies, like this one called NGC 1052-DF2, that have basically no dark matter at all. Now, according to the standard model, this shouldn't happen, ever. Galaxies are supposed to need that gravitational glue from dark matter to even form in the first place. And yet, there they are.
So get this, the vibrating universe theory doesn't just explain these weirdo galaxies, it actually predicts them. The math shows that some galaxies should form right on the universe's nodes. Those high vibration zones where matter gets pushed away. And here's the crucial part. The theory calculates that precisely 3.4% of all galaxies should be totally empty of dark matter. These impossible galaxies are actually proof that the theory might be right.
Now for puzzle number 2. Remember that bombshell discovery from the DESI instrument? The one that proved dark energy isn't some constant, boring force? It actually changes, getting weaker and stronger over billions of years. The standard model has absolutely zero explanation for this. It's a complete mystery.
But for this new framework, sometimes called the V8.0 theory, this isn't a mystery at all. It's exactly what you'd expect to see. If the universe is a vibrating membrane, of course its tension is going to change as it flexes back and forth. So while the old model predicted a boring flat line that completely misses the mark, this new theory predicts a perfect sine wave. And when you overlay the real data from DSI, it fits. It fits perfectly. The theory even nails down the exact timing of this cosmic vibration. The time it takes for one full beat of the universe's heart, 2 billion years. That is the exact rhythm that explains the rise and fall of dark energy that we're finally able to see. So okay, this theory cleans up our two biggest cosmic messes pretty neatly, but a truly great theory has to do more than just explain old problems.
It has to make a bold, specific, and totally testable prediction. It has to put its neck on the line, so to speak. If the prediction is wrong, the whole theory has to be thrown out. And that brings us to the ultimate crash test.
And the instrument that's going to be the judge, jury, and executioner for this idea is the SKA-Low, the Square Kilometer Array. We're talking about the largest radio telescope ever built by humanity, and it's set to start listening to the skies in 2027. Its whole job is to look back in time, all the way to the cosmic dawn, when the very first gas in the universe was just starting to form.
And right here we have a clear showdown. Two completely different predictions for what that telescope is going to see. On one side, the standard model says that this first gas cloud should be pretty uniform, more or less smooth. But the vibrating universe theory, it predicts something totally different. It says that the gas should have a distinct pattern of stripes, almost like ripples, a direct imprint of the cosmic sound wave that was pulsing through the universe at the very beginning of time.
And we're not just talking about some vague pattern. This is where it gets serious. The theory makes an incredibly precise make-or-break prediction. It gives us a number. It says that if the universe is truly vibrating, the SSK must detect a temperature fluctuation from those ripples of exactly 5.46 millikelvins. Not 5, not 6, 5.46.
So the million-dollar question is, can we actually detect a signal that faint? And the answer is a huge, resounding yes. The background noise of this incredible new telescope is only going to be about 1 millikelvin. That gives us a signal-to-noise ratio of 5.5. And in physics, anything over 5.0 is the gold standard for a formal discovery. This is it. It's a binary test. There's no wiggle room. The signal is either there or it's not.
This whole thing sets the stage for a classic, beautiful scientific showdown. It's more than just one theory against another. It's really about the entire process of how we discover truth.
And really, this is what science is all about. It's not about who has the fanciest degree or the biggest grant, it's about the data. As the person behind this theory said, the universe doesn't care if the right equation comes from a Harvard professor or an independent researcher. Only observation will decide. In the end, nature gets the final vote.
And so we wait. This theory gives us this beautiful, elegant picture of a vibrating cosmos. It solves our biggest puzzles, and it's laid down a clear, testable challenge. So come 2027, when the most powerful telescope we've ever built turns its ear to the dawn of time, are we finally going to hear it? The universe's 2 billion-year heartbeat? We're just going to have to watch the skies.